In this presentation, we will discuss the optimization of an electric vehicle suspension system for performance and cost. The system-level objective function is a normalized weighted sum of the objective function values of the three subsystems aiming to maximize overall performance while minimizing cost. The model will consider design variables such as a spring constant and damping coefficient, and it's based off of a model Tesla Model 3. The rationalization is that optimizing the design variables of a suspension system is necessary to a vehicle's design as it ensures the safety and comfort of the user while being most cost-effective for the company. The system boundary includes the suspension system but does not include the drivetrain, chassis, and the wheels. The three subsystems include the spring and damper, the suspension geometry optimization, and the spring material and material cost optimization. A couple variables include the spring constant and the spring damper attachment points, and there are no shared variables. As you can see, the system flow diagram is shown with the parameters and the variables defined on the right. Subsystem 2 feeds attachment points to subsystem 1, and subsystem 1 feeds the spring constant and the length of the spring to subsystem 3, which shows the coupling between the subsystems. Coupling occurs because changes in one subsystem affect another. By considering system-wide interactions, the optimization ensures the best trade-offs between comfort, stability, and cost, preventing design conflicts, and ensuring a well-integrated high-performance suspension system. Here is our system-level objective function, which normalizes each individual subsystem-level objective function using the upper and lower practical values and weights them and sums them together to create a 0 to 1 scale of how well our suspension is performing.
For the optimization model of subsystem 1, we have parameters such as the mass of the car and spring constant of the wheel, design variables such as spring constant and the damping coefficient, and a couple of variables such as attachment points, which will be used to calculate the length of the spring and spring damper angle. Some constraints to be sure that the system will behave accordingly, and an objective function that seeks to minimize the max acceleration felt by the user while making the system dampen time. Similarly, for the optimization model of subsystem 2, we have parameters such as roll center height, ride height, and maximum body roll angle, design variables that include camera angle and track width, and an objective function that seeks to minimize a weighted square sum between static camber and roll camber. We have here some constraints too, intermediate variables, and some linear constraints, which will all make sure that the system behaves accordingly. Finally, for the optimization model of subsystem 3, we have a definition of parameters such as shear modulus of the spring, its density, its free length, and the cost of the spring, design variables such as spring wire diameter, overall spring diameter, and pitch of the spring. The spring constant of the suspension system would be a coupled variable, and our objective function would try to minimize the total weight of the spring while ensuring maximum ride comfort for optimal spring stiffness. Moving on to system-level objective function mathematical modeling, we can see here that the system-level objective function will be obtained through a weighted sum of the objective function values for each of the three subsystems. To account for the difference in unit values of the outputs of each subsystem, we normalized the outputs of each subsystem and also added weights to account for the importance of each one of them. The normalization method was done by setting up a range of real-world values for each objective function and comparing how well the minimizations were being performed on these ranges, with a value closer to the lower bound representing a 0 and one closer to the upper bound being a 1. And the weights for each subsystem are represented here. Moving on, we can divide the types of design variables into local design variables such as spring constant, damping coefficient, camber angle, track width, wire diameter, and coil diameter, and coupling design variables such as the attachment points and spring constant. For the objective and constraint trade-offs, we know that having a higher camber leads to better handling but more tire wear. Having softer springs improves concerts but risks bottoming out. Lowering wire diameter lowers weight but also lowers stiffness, and lowering coil diameter lowers weight but limits packaging. Now, for critical constraints, we know that spring constant range ensures manufacturability and stability, damping ratio limits, maintains ride quality and safety, and bottoming out conditions protects the chassis.
We are using MATLAB software for this optimization. An algorithm were selected based on the nature of each subsystem. For subsystem 1, fmincon optimizes the spring constant and damping coefficient, which involves continuous, smooth, and differentiable function. For subsystem 2, GA handles complex nonlinear design variables, ensuring global optimization in the suspension geometry. For subsystem 3, like subsystem 1, fmincon is used here for optimizing continuous differentiable functions, particularly for spring material cost. Then at system level, we combine the result from all subsystems using a weighted sum balancing performance, cost, and other factors. The system model differs from individual subsystem models because it combines output from subsystems. Each subsystem influences the others, and their optimization is refined through an iterative feedback loop to balance performance, handling, and cost. Sprint length in subsystem 1 is a critical link as it is passed to subsystem 3 for calculating material cost. The interlinking ensures a cohesive optimization across all subsystems. At system level optimization, each subsystem independently optimized and iteratively design variables are adjusted based on performance and constraints. We choose fmincon for subsystem 1 and 3 because their problems are continuous and differentiable, while GA is used for subsystem 2 due to its ability to handle complex nonlinear optimization landscapes. The system level objective combines weighted results from each subsystem, ensuring a balanced optimization. Both fmincon and GA handle constraint effectively, with fmincon directly incorporating constraints and GA using penalty functions for violations. This holistic approach ensures that we find an optimal design that meets all performance criteria while balancing trade-offs.
Moving to the mathematical modeling part, for the first subsystem, we used a quarter car model with 2 degrees of freedom to simulate suspension behavior. Spring and damper forces act on both strong and unstrung masses, while road disturbance is modeled as an inverse pulse. We solved the equations using ODE 45 and added a constraint to ensure good ground clearance. The goal was to minimize acceleration tail energy. This subsystem models how the camber angle changes due to body roll. We assumed a fixed body roll angle and modeled camber gain linearly with roll center height. The objective was to minimize outward camber while keeping it under limits. We optimized two key variables, the base camber and track width. As shown in the graph, outward camber increases with roll center height, which helped us identify feasible zones. Now moving to the third subsystem, the spring cost optimization, where we use the stiffness value from this setup. This system focuses on minimizing the cost of a coil spring based on its geometry and stiffness. We use standard spring mechanics with material properties for steel. The stiffness value comes from subsystem 1. We used an equation for spring weight and a non-linear constraint to ensure manufacturability. This 3D plot shows the feasible region for spring design based on wire diameter, coil diameter, and stiffness. For the optimization results, this table shows results for 5 different optimization runs. We kept most conditions constant and changed only one parameter per run to check sensitivity. We tried key design variables like spring constant, damping coefficient, camber, and spring geometry. The system objective function stayed above 0.08 in all cases, which shows consistent performance across variations. The runs, we observed that changing clearance height and cost per kg gave the best improvement in objective function. Increasing pothole depth had a negative effect as expected. We also found that changing the initial gas for damping had little impact, which supports the robustness of the model.
In this slide, we'll look into constraint sensitivity analysis. This analysis shows that the system is highly sensitive to the lower bound of the wire diameter with the sensitivity of -3.5 to 5, meaning tighter bounds reduce performance. The mean diameter's lower bound has minimal impact and the wire diameter's upper bound has no effect. Relaxing the mean diameter's upper bound slightly improves the performance. Overall, wire diameter constraints are the most critical to system's performance. In this slide, we'll look on to the key findings from parameter sensitivity analysis. The depth of the pothole shows highest sensitivity, indicating its significant impact on suspension performance. The width of the pothole has minimal sensitivity, suggesting a lesser influence on the system's behavior. Change in roll center height showed moderate sensitivity. This sensitivity analysis highlights that optimizing pothole depth is critical for improving the suspension system's performance. Moving on to discussion of results, this slide reviews how realistic our system level optimization results are. For spring and damper, our optimized spring constant falls within the typical sedan values, and the damping coefficient is slightly higher than the industry norm, which likely shows reduced vibrations and improved comfort. For suspension geometry, the optimized geometry is physically realistic. Camber angle and gain meet the constraint, confirming feasibility. For spring material cost, while our model minimizes cost, it doesn't account for real-world factors like manufacturing tolerances, fatigue life, corrosion, material defects. So results are insightful but idealized. Our model produced feasibility, well-aligned results, but practical limitations must be addressed for real-world applications. Continuing with the discussion of results on subsystem to system optimality comparison. When we optimize each subsystem separately using suboptimal parameters and ignored variable coupling, we achieved a system level objective function of 0.78. However, when we move to full system level optimization, taking into account all coupled variables, the performance metrics improve to 0.84. This clearly shows that integrated system level optimization leads to better results by aligning subsystems more effectively. Looking at the future work, due to the scope of the timeline of this project, we had to simplify the model to make optimizations feasible. Future work would involve increasing the robustness of the system by including more realistic and detailed factors in each subsystems, using parameters that are closely matched to real-world automotive suspension systems, and further tuning the subsystem level model to push the performance metrics even higher. The goal will be consistently achieve an objective function above 0.9, which would represent a significant improvement from the current state of model. So while our model shows strong promise, there is a clear pathway forward for even better real-world applicability.